the urban water cycle. We continue now with Kim van Schagen. He will also give a presentation on the control of a wastewater treatment plant. Kim van Schagen is a consultant at DHV, and he is also did his PhD at the TU Delft, at the Delft Center of Systems and Control. And I give the floor to Kim.
Well, good afternoon. Talk in a microphone. My talk will be about a full-scale water treatment plant, and what we did there at this full-scale water treatment plant. We improved performance by using short-term water flow prediction. We did this research, or this implementation research, together with the water board of Salinisation, and together with a colleague of mine and two people of Salinisation. So what is it all about? The question we have to solve, or what we have to solve in these, what you want to achieve with the water treatment plants, is that you want to have minimal environmental impact. That's the most important thing. Of course, minimal cost. Cost saving is important. And not only during a study phase or during a troubleshooting phase, but you want to have it always. Not only today, forever. So what you have to do is not only improve one time the control, the central part of it, but you also have to monitor the control, like with an iWatt or something like that. But also you have to decide afterwards, okay, I have certain performance, what should I do now? Improve my control, or decide on I want other operational points. So that's the operational loop you should be in if you want to improve all the time your plant performance and your plant performance. And that begins, what I said, with to decide what is the objective of this plan, and use that objective and not something else to determine what is your control. What do you want to achieve continuously? And therefore are very important discussions: what is the objective and what are only the operational bounds, so what are the boundary conditions and within this plant should operate. And afterward, of course, monitor it, and of course decide, is it according to the objective, or does my objective doesn't fit. Well, now I will show a little bit more about control. If you go to a wastewater plant, you want the objective, of course, minimal environmental impact. And so what should you do there to achieve this objective? And if you look at wastewater, at the regular situation, the most important reason to have control at a wastewater treatment plant is to reject disturbances. You have all the time disturbances from your wastewater load, and you have to take care of that these disturbances will not end up in your surface water. And what are the disturbances? Of course, the dry weather load, and for the good viewers, they recognize the picture Alex used before. So that's a pity that was not in, that was in your presentations, else I could have showed it to you. And of course, for wastewater, it's also very important are the rain events. And so our hypothesis, our idea here was, well, if we know, we predict in drinking water, we do it already a long time. For wastewater, we can, in that sense, the same. And the same people are producing, which are consuming, are also producing the wastewater. So if you take the same prediction scheme as we use for drinking water, maybe we can improve plant performance by doing that for wastewater. So predict wastewater load, in that sense only wastewater flow, and assuming constant concentrations. That's again a consumption. And well, how do you predict? You say, well, in history it was like, yes, I heard a nice term, historical prediction it's called. So based on historical situation over here, so this is what happened in the past days, you of course know what the next days will do. That's, people don't change that quick their behavior. And of course you have to validate the data in case of some situations which are not common, you have to say, okay, this was a strange day, but you can quite easily recognize the pattern of normal dry weather load. In that sense, you have an adaptive forecast of your flow for the next 24 hours. Well, we did that prediction, so we wanted to test if this prediction would really improve plant performance. And of course, you want to do that at a full-scale situation because there you have the real situation. And we were so lucky that water for line aim found it also very interesting. And we started at the city of Soest, where they have two identical treatment lanes for wastewater. Maybe you can recognize on the picture. There's one carousel here, and one carousel there, and also the clarifiers were also split into separate lanes. So there's really two separate installations which get the same wastewater load. They thought over the two lanes. Each lane has two surface aerators. The surface aerators are used to bring oxygen into the water, and that stimulates the biological process to remove ammonia and phosphate. There were continuous measurements of ammonia, nitrate, and phosphate, and the plant was available for a test period in June and July of this year. And what we wanted to test was three control strategies. To begin with, it was a fairly dated installation, and they had only oxygen control. So very simple oxygen control, an oxygen measurement, some kind of PID controller, which determined how much oxygen, how quick the aerators would blow and how much oxygen was entered into the water. Well, the first control scheme proposed by the water board, and which was quite common at other installations, that we say, well, we extend this one simple control loop, which they trust very much, and say, well, my oxygen set point is not fixed, but I change it during the day based on what my ammonia measurement is. Ammonia is one of the important values which have to be kept below a certain value. And then a fixed ammonium set point, and this ammonium set point was very conservative. And why? Because they say, well, if it's too high, we have chance of phosphate release, and then we have a problem with our phosphate concentrations. So phosphate was not in the control loop, but they decided on changing ammonium set points based on this phosphate boundary conditions. And then we said, okay, let's turn all the world upside down and say, well, what is the main thing you want to control? Well, the main thing I want to control is ammonia. So why not directly control ammonia? And I said, well, there's a boundary condition. I want to have a limitation of phosphate. So why don't you bring in phosphate in this control scheme? So mainstream is ammonia, but if phosphate gets a problem, it takes over. And the next thing is you say, well, I know something will change today because every day is the same in that sense, and we can predict what will happen. So why don't we take in this information we have already and bring it into the control scheme and change my aeration based on my predicted flow? So not wait until ammonia is too high and then run after it and try to repair the error that occurred, but start aerating before that ammonia increases, because I know today the load will increase. It's quite a trick to get. Okay. So, and of course we wanted to try to have a fair comparison between the three control strategies. Well, the oxygen control was there for all the time, so we had a lot of historical data about that one, so we didn't have to bring it into our test scheme. What we then did was for the two lanes, we did every week we switched the two lanes for oxygen, cascade control or this predictive control. So the cascade control is ammonia, oxygen, aeration. We started off with both lanes on the same control to compare, okay, if the control is the same, they should behave the same. And afterwards we flipped them on every week, and that for in total 5 weeks. So you see the scheme here. So then the results. to begin with, of course, we want to see is this behavior, which is quite common in drinking water. 1/3 of the Netherlands has already a scheme like this. So is this scheme also for wastewater? Does it hold? Well, not very astonishing, but also for wastewater you can very commonly predict the dry weather load. So this is the dry weather wastewater load of the people living in Soest. And as you can see here, for the people that can read Dutch, on Tuesday it rained a lot, and you even can calculate in the supply area how much rain has fallen. And the same here also. So two things very easy to see. You can see normal dry weather load, so for optimizing the normal situation. And on the other side, especially during low dry weather flow, you can easily see that at this moment it starts to rain already. So you already, rain events is for wastewater installation more like, okay, now run like hell because you won't make up for it, go. So if you detect rain, start all aerators and hopefully you will hold during the rain period. So in this case they already can start here by full capacity because they know it has started to rain and we have to treat all the water coming. So if you then go to the three control schemes, we use this cycle of controlling, monitoring and deciding. Well, first of all, to explain these three the same sheets. This is more to this where you can see what the decision is. They say, well, I have nitrate on this axis and ammonia effluent concentration on that axis, and my target is I want to have my treatment plant inside this green rectangle. That is the place I think my plant is running well. If it goes to yellow, it's not so good, and the red part is I don't want to be there. So that's the decision that is made. Now, what does this do? Is say, well, for 1 week of operation, I draw a dot which the size of the dot is equally big as the period in this week you have been in this situation. So you see that, of course, not so strange, in the case of oxygen control, there's no relation to ammonia. The oxygen control merely kept nitrate at a certain level, but ammonia went all the way, which is not strange because it was not in the control. So they were happy, of course, when this happened to say, well, everything is within the green, and in fact, it's what we wanted to achieve for. But then if you go to predictive control, what you see is that you even can narrow down the range of ammonia, and which is the main target. And in the sense, and at that point they are now, you're doing too good. So this line here, this 1.5 ammonia, can go up a little bit because that's inside the situation where you want. And as soon as you bring ammonia a little bit up, you even save more energy because you don't treat that part of water you don't want to. So that is in this way. And if you then look in more detail what it means for this predictive control situation, this is a graph of the controller itself, and I hope to explain a little bit how the prediction works. So there was a flow prediction, and we saw that earlier. And this flow prediction on the bottom part is really translated in this purple line. Okay, if there's this flow, this is the amount of aeration that's necessary in a normal situation. Of course, you measure, this is 1 day. Of course, you also measure ammonia. This is the red line here. You see it goes up a little bit around this 1.5, which was desired. And what you do is say, well, I follow my prediction, except for the case that ammonia is too far off. And what you now see is that you don't need big perturbations of ammonia, and you already start decreasing or increasing aeration. And that helps preventing that you over-aerate, because as soon as your ammonia gets so high, you have to overtake or to compensate for the too much ammonia and control it back to the normal value. Because you are reacting already on the estimated flow which is coming, you don't wait until ammonia is gone up. And that helps you also saving energy. So your control is less extreme than if you would only go to ammonia control. So what we, of course, then compared also, most important part for them was, okay, ammonia is a flat line. That's what we want. Second part, of course, is the cost. They want to reduce costs. So this graph with a lot of numbers is interesting to read. You can read in the paper, but in a graph it means like this. So you have these 2 weeks, and we say, well, in week 0 we had the same energy consumption, which is of course logical. We're the same control schemes, and then in these 3 weeks we switched around between one lane and another lane between the controls, and then compared which one of is it the predictive control or the cascade controller, and you see that consequently the cascade controller uses more energy to achieve the same goals. So in this situation where you even see that ammonia concentration at the end is lower, even then you have a saving of about 3.5% of energy. So to conclude that is that you can predict your disturbance of your plant, of your wastewater plant. You know what's going to happen, so it's good predictable. You can integrate it in a quite simple aeration scheme, and that helps you keep your effluent concentration constant and close to what you want to achieve. It helps reducing energy. And the nice thing, it's very understandable for operators, because experienced operators work in the same way. They look to yesterday and the day before and say, well, normally this happens. Okay, today I do something like that, almost the same. And a very important and an important effect is that you can really quickly detect a rain event, and really before even at the first drops of rain, without rain apps and rain radars and stuff like that, already detect, okay, something is going on, I have to aerate. So thank you for your attention.